Well, good morning, everybody, and welcome to the latest Collision Hub webinar this morning from Miller Electric, talking about MIG welding, GMAW welding for collision repair. Appreciate Ace joining us today to talk about some basics, some fundamentals, and some troubleshooting. So we're going to have a series of three actually Miller webinars. So first, I want to thank Miller Electric for sponsoring this. It's great to have. I've worked with the Miller guys for a long time, and they're always fantastic. And it's great to be kind of back in the collision world a little bit more focused on there. So I'm going to introduce you to somebody at the end of the presentation today, if he's able to make it. He's in our meeting right now, but we've got a collision repair person at Miller now to help us out with something. So hopefully he'll be able to join us following his other meeting, and I can introduce everybody to you and let you know, introduce everybody to him. I also want to thank Miller honestly for their support of Skills USA. It's not part of most of these webinars that we've been doing, but Miller's been a huge supporter of Skills USA, both on the collision repair side, certainly the welding and welding fabrication, and even on the welding sculpture contests that are out there. So many thanks to Miller Electric for their support of Skills USA, which is a fantastic organization. If you're not involved with your local Skills USA group or state chapter, I'd love to have you get involved in that too. It's just a fantastic organization that you'd love to be a part of. So we're using the webinar feature today, so you won't be able to take yourself off of mute to ask questions. So if you do have questions, at the bottom of your screen, you can either use the Q&A function or the chat function. I'll be monitoring that throughout as Ace covers his content today. So with that, Ace, why don't you go ahead and introduce yourself and tell us a little bit about what you do and who you are, and I'll let you take it over from there. I'm going to go dark, and it's the show is yours.
All right, thanks, Jason. All right, so a little bit about myself. I'm a weld engineer with Miller Electric. Been working here for about 5 years. A lot of what I do is machine development, arc development for machines. I'm a car guy myself. I did a lot of car restorations growing up. Still do a lot of car restorations. Currently working on an old Ford Bronco. That's pretty fun. So anyways, today what I'm hoping to do is mostly talk about gas metal arc welding 101, short circuit transfer. Like Jason was saying, these presentations there's gonna be a 3-series presentation, and it's gonna build on each other. So if you can, try to join all 3 of them, and we'll get some of the basics down today. We're mostly gonna be focused on talking about welding on steel. First off, I want to talk about some safety. I'm going to talk about the GMAW process for those, just to maybe give you a little view on what's happening while you're welding. Next, we're going to talk about selecting the right setup for GMAW short circuit on steel, how to set up a welder for GMAW on steel, some welding terms and techniques, and tips for troubleshooting, or tips for thin gauge steel, and also some troubleshooting techniques. So first, safety. I always like to bring this up. Always protect yourself. When you're welding in your shop, always make sure that you have a welding helmet on. Typically, it's good to use a shade 10 or darker. Make sure you always have a jacket on. I watch a lot of car shows, and seems like guys don't like to put their jackets on, but what can happen is that welding arc is so bright that it could give you sunburn. So make sure that you do take those 10 seconds and put that jacket on. Also gloves, protect your hands from the heat, and lastly, safety glasses. So real quick, just want to touch base on what is GMAW. It stands for gas metal arc welding. A lot of people call it wire field welding or MIG, all terms that get thrown around a lot. So it's a process that uses a constant voltage power source and a wire feeder, and the wire continually feeds through the gun from the power source, and when it makes contact with the weld metal, it creates a short, and that's where we get our short circuit transfer. Before I jump into a video that I want to show you guys, I'm going to show you just a basic makeup of a setup for GMAW. So first off, we have a bottle of shielding gas. We have a flow meter or regulator up here. Then you got a line coming off your regulator that goes to the back of the machine. That wire feeder power source, inside you'll have a spool of wire, and then a drive motor that pushes that wire through your MIG gun. And then you'll have a work clamp that comes down, connects the workpiece. Now when the wire comes out of that MIG gun, it'll make contact, and that's what's going to create a short. So in this video, you're going to see a slow motion of the arc. It's going to zoom in right on the end of that MIG gun. And essentially, I just want to show you what is actually happening. So right now, welding, this is what it'll look like normally. Now in slow motion, you can see that wire comes down, makes contact, and there's a little bit of an explosion in that short. The arc stays lit across there, and it begins to melt the end of the wire again. So that can happen anywhere from 90 to 200 times a second. So that's where when you are welding, you get that nice crisp buzz. All right, so moving on, let's talk about selecting the right setup for GMAW on steel. First thing I want to talk about is shielding gas. So a really common shielding gas to use is C25. It's 75% argon, 25% CO2. Using this shielding gas, it'll give you arc characteristics of a smooth arc. It's nice and crisp. It also affects your bead profile, gives you a nice flat bead face. Another really common one is C100. What you'd see, the difference between a C100, which is 100% CO2, and a 75-25 mix, is you're gonna see a little bit harsher arc with C100, but it does have a deeper penetration profile, but it is a little bit cheaper to use. So whenever I'm training anyone on beginning to weld or things to know about welding, one of the things I like to do is pull up a picture of a spool of wire, because basically you need to match your shielding gas to your wire to the application to what you're welding on. So if we're welding on steel, a really common wire to use is ER70S6. Now it does require gas shielding. There's a bunch of sizes that it's available in, but really common ones that you'll see, 023, which is the same as 024 and 025, 030, 035, and 045. For auto collision and auto repair, people really like to use these two because you can really limit the heat input that goes in with 023 wire. Now, one of the things I just wanted to do was look at the picture over here on the right and point out, no matter the brand of the wire or the type of the wire, it's always going to have a few different things. So you'll be able to tell the type of wire that it is. So there's our ER70S6, MIG solid wire, and then it's going to tell us our diameter of that wire and the weight of the spool. So just important to know, those are the things that you're looking for when you're selecting wire. In other presentations, we're going to be looking at aluminum, we're going to be looking at silicon bronze, and how to determine those as well. After you've selected your shielding gas that you're going to be using, you've selected your wire you're going to be using, you need to select a drive roll to use. Now I pulled up this picture because there's a whole variety of types of drive rolls. When we're welding on steel, we want to use a V-groove drive roll. And what that is that's actually the shape of these grooves in there. A knurled is typically used for flux core. Then typically you'll use a U-groove for aluminum. But we want to stick with these ones when we're using steel. Essentially, size and type is key. So type of drive roll, it's a V-groove, and we want to match it up with the diameter of wire that we're using in the welder. Next thing we want to look into is matching up our consumable sizes. So on every single contact tip, it doesn't have the writing on this one, but there will be lettering on there or numbering that'll tell you what diameter that contact tip is. And it's crucial that you keep that the same as your wire diameter size. All right, so let's jump into setting up our machine for welding. Just real quick, I like to reiterate the importance of making sure your wire diameter Once you have that selected, matches your drive roll size and type. One thing I didn't talk about was your gun liner. So gun liners are interchangeable. You can get different diameter gun liners. You want to make sure that that matches that wire diameter that you've selected, and then also the contact tip size. So typically the first thing I'll do when I'm going to set up to weld is hooking up my gas. Really, really important. Like you can see in the picture on the left, top left there, this cylinder is chained to the wall. You always want to make sure that it's either chained to a cart or it's chained on the wall. Make sure that it's secured, because if that cylinder does fall over, that regulator can break off, and then those are under such high pressures that it could hurt you or could hurt one of your coworkers. So be really careful with that. Next, what you want to do is that valve on top. Before you hook on your regulator, you want to just open that quickly and close it. It's going to let a little shielding gas out, but that's going to clean out any dust that you have built up inside. Then what you'll do is you'll thread in your regulator, make sure that that's nice and tight. You'll see that these two gauges, there's nothing on. Once you turn on that bottle, as long as this flow meter adjust knob here is loose, you won't see anything show up here. But once you turn on that valve and you start tightening in your flow meter adjust knob, you're going to see this gauge will show you the pressure that's in your tank or your cylinder. Apologize. The one on the left here is going to be your flow meter or your flow gauge. And what that's going to allow you to adjust is your cubic feet per hour. Really common, what's really good to set it to is 25 to 35 cubic feet per hour. If you go too low, you might start running into some issues like porosity. If you go too high, you still will have issues. It creates a turbulence in the displacement of the shielding gas, which can also cause porosity or other issues. So something to keep in mind, make sure you have that set correctly. It really does affect the weld quite a bit in the welding arc. Next up, I just wanted to show one thing that's really important is when you go to install your MIG gun, you'll put it into the drive motor here, slides in from the front. Always make sure that you seat that drive gun in. The power pin is what I typically call it, and that's that brass piece. Make sure that slides clear in, and then you tighten it. No matter the welder, it's always going to have some type of way to secure that in. As long as you want to make sure that's clear up in, because otherwise you could get some shielding gas leaking out of here. Then you might have some issues like porosity. Next thing you're going to do is hook up the pins for the trigger on your MIG gun. So once that's connected, you can go ahead and install your wire. First thing I like to do is make sure your spool hub tension is correct. So that's going to be, so this is our spool hub here. We got our spool already loaded on, tightened with this nut here, so it's secured in place. And then there's always going to be some kind of tensioner here. No matter the machine that you have, there will always be some way that you can either put more drag or less drag on that spool as it's feeding through. So what I like to do is just kind of test that by hand, make sure that it's not just free spinning, or that it doesn't continue to spin after you let go of it if you spin it a little bit. And usually also, because what happens is if it's too tight, it won't allow you to feed wire through. If it's too loose, when you stop welding, this will continue to spin. All right, so next up, you want to feed the wire through the gun. Then what you do is install your contact tip and put on your nozzle. What you want to make sure there is, and it's key when you're setting up your welder, is make sure all your connections are tight. So when you're putting that contact tip in, take a set of pliers and just snug it up. You don't want any loose connections, or you will probably see an arc performance difference. So you might see some degradation there. Once you've fed the wire clear through the gun, you can go ahead and you can set the drive roll tension. Now, when I'm talking about drive roll tension, I'm talking about this right here. So the tighter we make that, the more pressure it puts down on these two drive rolls. And what you want to do is you either want to take a piece of wood, or sometimes I'll just use a glove, and I'll put my hand towards the end of the gun and just curl that wire on my glove or on a piece of wood. And you just want it so it doesn't slip. You don't want these drive rails to slip as you're feeding that wire through. You don't want them too tight or it's going to bog down your drive motor. So just something to keep in mind there. Then always, I apologize, I didn't get a picture of the polarity connection set up or installed here, inserted here. But for welding on steel with GMAW, we're going to want to make sure that we use DCEP, which is direct current electrode positive, for our polarity. And whenever you're looking at what polarity you should use, typically if you open the door on the side of your welder, it'll have a little indicator there on how you can select your polarity. Otherwise, look in your owner's manual, and that will always give you a recommendation on how you can change that polarity and how you should have it hooked up. So for different welding processes, you'll want different polarities, but for welding on steel with GMAW short circuit, we want to use DCEP. So one analogy I was thinking of is if you have the wrong polarity and you do start welding, it might weld, but it's not going to be optimal. It's not going to be what you were hoping to get out of it. Just like if you were to take your car and you swap your spark plug wires, it's not going to run the same as when it's in the correct firing order. So once we have our welder all set up, now we're going to start making some adjustments. So these adjustments are parameters, and those can be adjusted on the front of the machine. So every MIG machine or gas metal arc welding machine is going to have at least 2 adjustments, and that's going to be voltage and wire feed speed. Wire feed speed's measured in inches per minute, and basically those two have to be dialed in together so you get a nice, crisp, smooth sounding arc. I pulled in a little screenshot here of a parameter chart that I just wanted to point out and kind of go through a little bit, because as manufacturers, they will always develop parameters for a good starting point, and you can adjust from there. So usually they read from left to right. So welding on steel, using electrode positive polarity. If we were using 7525 or that C25 gas, we would look here. We got ER70S6 wire. And let's say we want to weld 16 gauge with 030 diameter wire. We'd go to 030, move over to 16 gauge. That would tell us we need to set our voltage to 15.7 volts and our wire feed speed to 226. And that's going to give us a good starting point to start welding. So let's talk about voltage just a little bit. So it's adjustable on the front of the machine. Some machines might point out that you can actually read what voltage it's set at. Some might be a scale of 1 to 10. No matter what, you'll always have that parameter chart that you can base off, get a starting point off of. So with our voltage, too little, it directly correlates to our bead profile. And if we have too little, we're going to get a really ropey bead. It's going to build up quite a bit. When it's set right, it'll be washed out like we want it to be. But if we get our voltage too high, what can happen is it increases our arc length, which is from the end of the wire to the weld puddle. It can get too wide, and it can start to change transfers, which we won't talk about transfers now, but we'll talk about them in one of the next presentations. So the other adjustment that we can make on the front of the machine is our wire feed speed. So what wire feed speed directly correlates to is our amperage, and it affects the penetration that we have into the base metal. It also affects how big that weld buildup is. Because if you're thinking about it, if you're adding more and more wire, you're getting a bigger weld. And it's also measured in inches per minute. So next up, let's talk about some welding terms and techniques. So in this diagram, one of the really common terms that are talked about is contact tip to work distance. It has a big effect on your arc performance. So just talking through this picture here. So we have our nozzle is on the outside here. We have our contact tip, and then we have the wire that comes through the contact tip. And then we have our weld puddle, and then our work piece here. So contact tip to work distance is the distance from the end of that contact tip to the base metal itself for the weld puddle. So typically you want to keep that fairly tight. You want to keep it about 1/4 inch to 3/8. Typically when you're welding on thinner material, you'll really want to keep that closer to 1/4 inch. But that'll help you maintain a very smooth and crisp arc. You start getting too far away, you might see some issues. You might get some sputtering and potentially you start to lose a little bit of current, and so you lose a little bit of penetration that way. It cools off the arc a little bit. Next, I want to talk about push-pull angles. So still similar, so nozzle, contact tip, and all this is really talking about is the way you hold the gun and the direction that you're welding. So if we're welding from right to left, if we're pushing, we would be basically pointing the wire towards the left. Perpendicular, straight up and down, and then dragging would be pointing the wire towards where you started the weld and then moving forward. So typically with MIG, if you're wanting more of a flatter bead profile, you would make sure that you want to push the puddle. Dragging might have a little bit more buildup. So the next angle that I want to talk about is our torch angle. So we have our nozzle, the wires coming through, and what'll happen is basically wherever you point that wire is where the weld is going to end up, where it's going to flow out. So this is what I really like to show this picture, because there's 3 different welds here. The first weld, we're on a horizontal T-joint is what we're on right now. We have the gun basically at 45 degrees. So what our goal is to get half the weld on this bottom plate and half the weld on the top plate. And we want to maintain a nice travel speed, which we'll talk about in a minute. But we want to make sure that that weld washes out onto both pieces. So on the second one here, we tilted the gun down a little bit and it pushed that weld bead up onto that top plate, and it didn't really penetrate or wash out onto that bottom plate at all. So this weld here could potentially break pretty easy. This third weld's a little bit harder to see, but essentially it's the opposite of this setup here, where the gun was pointed more towards the bottom plate, and so it didn't wash up onto the top plate there like we wanted it to. So like I said a minute ago, the next thing we want to talk about is travel speed. So travel speed is, as we're moving down this weld, the faster we go, the smaller the bead will be. The slower we go, the bigger the bead will be. We want to make sure that you maintain a smooth travel speed, consistent, while also keeping that contact tip to work distance nice and tight between 1/4 inch and 3/8. So I got a couple welds here we can kind of look through and talk through. So first off, this is a good looking weld. So this is on thicker plate. This is another horizontal T-joint. So as we can see, we got even distribution onto both pieces of metal. We got a smooth bead face. So as we're looking down this, it was a nice and consistent weld. Nice and smooth. Also, one thing I want to point out, you might see a little bit of spatter every once in a while, but that's these little metal balls that are on the plate. Micro spatter is okay, which is really, really small spatter, but you want to be careful that you don't have really big pieces of metal on there, or really big pieces of spatter on there. Next one I want to check. All right, so let's look at this weld. So to me, this weld looks a little ropey. It doesn't quite wash out at the toes like we wanted it to. The bead profile is very convex, and as we're looking at it, it was an inconsistent travel speed. The weld's a little bit bigger here, then it gets smaller, and then it gets a little bit bigger here, a little bit smaller here, and then back to being big again. The other thing that we wanted to look at was penetration profile. So basically what was done with this weld is it was cut and then looked at from the end view, and we can actually see that because the parameters were probably not correct, that it didn't penetrate very far into this plate, which means that's bad weld. All right, so next up, I want to talk a little bit about some tips for welding on thin gauge steel. So when I'm talking about thin gauge, I'm referring to from 14 gauge to 24 gauge. Usually when I'm welding on thin gauge steel, if I'm replacing a body panel or I'm welding in a new piece in a fender or something like that, I want to make sure that I'm using short welds. And I definitely move around quite a bit so that I try to limit the distortion of the sheet metal, because the thinner the material, the easier it is to like distort and bend. And I got a couple pictures here. So here's one little example. This is a vertical up butt joint. I did a couple short welds here, and then I moved up, did a couple short welds here. And then if that was a patch piece in a panel, I'd be bouncing all over the place to try to limit that heat going into it. Just as an example, I did a weld butt joint again did it in the flat position here, and I just ran a bead across here. What I wanted to really show was that distortion, that heat input. If you run a continuous weld across there, it'll really put a bow in your metal, and you can see that here. Back when I was in college and just got out of college, I was working in a fab shop, and we worked quite a bit on Jeeps. And one day we had a new guy working for us, and he went to go weld in. We were doing a quarter panel in the Jeep, and he went to go weld it in. And instead of bouncing around and doing short welds, he just welded right across the side of the Jeep, and it ended up putting a big wave in that Jeep. So that picture on the right really shows that the curve that I put into that metal. So lastly, one of the things that I really want to talk about is troubleshooting. So I got this picture here, and basically what the recommendation there was, make sure if you're starting to see something weird or something's not working correctly, make sure that you inspect everything that you have. Make sure that everything's correct, set up correct, and that it's clean. So this nozzle here has a lot of spatter on it, a lot of buildup. And so you got to keep that cleared out so that your shielding gas will flow through and protect the weld protect the molten puddle from the atmosphere. So first things I always like to check is just making sure that the polarity is correct. You have the right polarity for the process that you're welding. You have the right shielding gas, the correct contact tip size, that it matches the wire diameter that you're using. And contact tips do wear out. So if you're starting to see something in the arc, make sure that you first thing, easiest thing to do is swap out your contact tip. Next thing I like to do is just double check the MIG gun, make sure that it's inserted correctly. Double check your wire type and size, make sure you're using the right wire for the application. Make sure that your drive roll tension is set correctly, and that you have the correct drive roll size. One thing that I did want to point out is, so a lot of times when we're welding on automotive stuff, we want to make sure that our material is prepped and clean. So if you're doing a collision repair and it's already a painted part, you want to make sure that you get all the paint off of that part. before you go to weld. Because what that can do is that can pull the paint into that weld and it'll contaminate it. And you might see some bubbles in the weld, which is called porosity. There's some other issues that can cause porosity, one of those being lax shielding gas. And also what's difficult on cars now is that as you're going to weld, you might prep the outside of the material or the one that you can get to right there, but there might be some kind of coating on the inside of the panel that you have to be cautious of as well. You don't want to draw in anything from the backside there that can contaminate your weld. One tip that I have is to prevent your spools of wire from corroding. When they're left in the atmosphere, your wire can basically get contaminants on it, or it can rust when it's just sitting in the atmosphere. Here in Wisconsin, it's really, really humid. You have to be careful about that. And so when you're not using that wire, I always like to recommend that you pull that wire out of your machine and then you wrap it up in a plastic bag to protect it. All right. So Jason, maybe we can move and talk through some questions.
Yeah, so again, everybody, if you have any questions for Ace here, please use the chat or the Q&A function, and we'll try to get those addressed for us. So Ace, one question I've got, when it comes to, you know, push versus pull technique, does it matter? Do you have a, do you have a is it a personal preference, or are there reasons why I would use one over the other for steel welding?
For steel welding? Yeah, for short circuit, you can use either. Typically, what I've seen is if you're pushing the puddle, it can help to wash out that weld bead a little bit. If you're dragging or you're pulling the puddle, it can cause a little bit of buildup. And so typically I go with a push route.
You go with what? I'm sorry, push?
Typically I'll push the puddle, yeah, when I'm welding on steel with.
And then that would be great, because there's some you have to use the push technique as well. Is that
right
for other materials?
Right. Yeah. So like if we were talking about aluminum, you always want to use a push technique because you want to get your shielding gas out in front of the puddle to protect it.
We got
we'll talk about that more.
Do have a question coming in here. What causes too much burned appearance on a weld? So I'm not sure if that's you know, a large heat affected zone, or what was it? But what causes too much burned appearance on a weld? Dave, if you could maybe clarify that, if you're looking for, again, that heat affected zone around the weld or something different, that would be probably helpful, I think, for Ace here.
Yeah, maybe I went back a couple slides. Maybe one thing we can look at.
Yeah, all around the weld. That's a perfect slide for it. Yep, right there. So
as we're looking right here, you kind of see this discoloration around that weld right there. And basically that's a heat affected zone. So no matter what, when we're putting heat into that plate and we're melting metal there, it's going to cause a heat affected zone. Now, if that parameter is too hot, like let's say our voltage is too high, or our amperage or wire feed speed is too high, that's going to cause that heat affected zone to be even larger. So that's why it's really important to, one thing, yeah, I didn't talk about this and I kind of did, so this kind of helps me out a little bit, but a lot of times I'll go into shops or I'll go talk to guys and they're like, well, I set the welder on 1 voltage and 1 wire feed speed, and that's what I use for everything. But really what you want to make sure of is that when you are welding, let me see if I can jump back here. All right, back to this parameter chart. So all of these parameters are dialed in, are good set points for that material thickness. And what that's going to do is that's going to help you limit that heat input. So if you're welding on, I would recommend looking at your welder, looking at the suggested parameters. And if you're welding on 18 gauge, but your parameters are closer to 1/8 inch, you might be putting too much heat into that weld, and that heat affected zone is too large. Excuse me.
Yeah, I think that's a great point as far as you can use in the chart that, and they're on every machine, right? So I think one thing, Dave, that we run into, and I know I'm guilty of it, I think when we all first started learning to GMA, you know, MIG weld, and you know, if you look at any publications, any books that are out there, a lot of those are designed for thicker material. They're not designed for automotive applications. And so they're always talking about making sure we get good penetration in there. Well, that was okay on mild steel vehicles, and we were talking about, 16 or 18 gauge even, on those materials where we're really trying to get in there and burn it. But now that we're dealing with, 22 gauge material and thinner materials, that heat effect on these ultra high strength, higher and ultra higher strength steels can really cause that warping, that distortion that we're looking at there, can have an adverse effect on the heat affected zone. It's one of the reasons why we're seeing some more MIG brazing applications, is again, to kind of control that heat. So when we're dealing with today's vehicles, when we're, again, maybe not so much on a plug weld, but maybe certainly on an open butt joint, or even a butt joint with backing, or a fillet weld, we want to control that heat. And so we're going to make sure that we're using, some heat control techniques, so we're not getting that large heat affected zone, because again, not only is it damaging the metal, but it's also, removing some of those potentially corrosion protection qualities that the steel might have if it's got a zinc coating steel on it. There's another question came in, but while I read that one and try to analyze it, one thing that I've got a question, if you can go back to your hood chart again real quickly.
The parameter chart?
Yeah, the parameter chart, yep.
Yep.
Okay, so a lot of times I'm welding a thinner material to a thicker material. So if I've got maybe an outer panel that I'm welding to a reinforcement, how do I account for that? So let's say I'm welding a 22 gauge panel to an 18 or 16 gauge panel. What parameters should I be looking at? How should I approach that?
So whenever I'm doing an application like that, I want to take and I highly recommend this, go and get a couple scrap pieces of metal and do a practice weld first, because this is a very good question. And typically what I'll do is I'll take my practice materials that I've got, my practice pieces of metal, and sorry, you were saying 22 gauge to 18 gauge?
Yeah, just hypothetically, I think this is pretty good.
Sometimes I'll just take and split the difference.
Okay.
And so I'd grab the 20 gauge parameter and just look at that, maybe test it out, see if it works. Also, you'd want to focus the heat a little bit more, or focus that weld a little bit more onto the thicker material.
Okay, perfect. I had a follow-up question to that, and I completely lost it. So Dave's asking, again, my older Miller 210 doesn't have the digital readout, so what would be best setting for 18 to 22 gauge? Again, looking underneath that, under the, I don't have the right, I'm using the right term, Ace. I'll lift up the hood and look for those, and it's going to give you your voltage and amperage starting parameters on there, and then kind of fine tune from there. Would that be correct, Ace, to say?
Yeah, exactly. So yes, not all machines will give you the digital readout, but still there should be parameters on the inside there in the door chart.
Yep. And one thing I love and I get about the Miller-Matic machines with their auto set feature, I know that Ace covered the auto set a whole lot on here, but that feature on the Miller-Matic machines that are out there is fantastic, because it'll get you right in here. So if you put your electrode wire and your electrode wire size and material thickness on there, it's going to dial these settings right in there to these recommended parameters to start with. And again, we can fine tune from there, but I absolutely love the auto set feature. So I'm not sure who came up with that concept at Miller Electric, but they certainly deserve some kudos for that. All right. Any other questions coming in? I got nothing here. And I don't think Joe joined us, so I can't introduce him, unfortunately. So again, he's in another meeting, one of those long meetings that I certainly don't miss. And thank you, Kristen, for not having a lot of those 2, 3, 4 hour web calls. I know you don't like those either, but so unfortunately, Joe Lay is not able to join us today. Hopefully, he'll be able to join us for our next Miller Electric presentation. But Joe is kind of the new collision guy at Miller, so it's good to have an industry guy that's been in the industry for a while with Miller Electric now, and Ace and Chris Rail and the whole crew at Miller Electric has been great to work with for many years. But now they're really kind of I think they're focusing a little more on collision once again, that they maybe hadn't been as active in for the past several years, but they're getting back and active in that. And again, Joe is the guy, and I don't have his contact information in front of me to share with you, but if you do want to reach out to Miller Electric for any questions, any information, I can pass along your information to Joel or get in touch with Ace. If you've got anything out there, they make some fantastic equipment. So I guess if there are no other questions, Ace, I just want to again thank you for your time and effort this morning and sharing some great insight for us. And our next, when's our next one we got here, Ace? We're a couple weeks, right? We're at, next Wednesday, right? 11 a.m. next Wednesday?
Yep.
Cool. So again, visit the Collision Hub website for the link to that. It will be again at 11 a.m. Central Time. And we'll be talking about some steel welding best practices at that time. So I look forward to having you there with us again. So again, Ace, thank you very much. Thank you to Miller Electric for sponsorship of this webinar today. And I hope everybody has a great rest of your day.
Awesome. Thank you, Jason.
You bet. Have a great day.
Thanks, everybody.
Bye-bye.